So this is more chemistry here than anything else. So be focused on the chemistry, please. And there are a lot of chemistry involved, but I will try to make things more easier to understand. So when we talk about the material synthesis, there are a number of processes that you come across. Now, in fact, we are doing chemistry everywhere, whether we are working at home or in the laboratory. So when you talk about this, we normally think that what are the best way to make the materials. So the best way of the make the material which is environmental benign. Why we are talking about these materials? Because if you see this particular slide, so the energy consumption is increasing day by day, and this is probably not visible properly here, but I would say that the solar energy and solar, wind and renewable is the energy which is having the future. So if you can see from by 2050, the majority of focus on the solar energy. So but solar energy is not something that you can store. You require materials, and for materials you require synthetic procedures to make them at large scale, which is industrially viable, can be scalable. Everything, whatever material we make in the lab may not be industrially scalable. So we have to identify the processes, and to understand the process we need to understand the chemistry of the process. So extensive research is required for the new materials. The materials to conserve the energy, to store the energy, and more importantly, synthesize at large scale with controllable morphology, size, composition and structure. This is a key when we talk about the material synthesis. And this material is not something once you make and you cannot reproduce it. So the reproducibility has been a big challenge in the material. So this is one of the important things that we have to look into. Cost effective. So if the material is so expensive that you cannot afford it, that material will not serve the purpose towards the energy. I give the simple example. When we talk about the lithium-ion battery which is used in the car, now how much time a car required to get charged? 5 hours, 6 hours. And how much time you require to fill the gas in your car? Hardly 5 minutes. So if you have a car which battery can be charged in 5 minutes, people will buy it. You cannot stand on the pump or the charging station for 5 hours. That's the one of the reasons. So for that purpose you require the fast charging batteries. For fast charging batteries you require materials which can help to do the fast charging of the lithium-ion battery. Since such batteries are not existing till this date, the battery operated car is still not in practice because acceptability is poor. So the material preparation towards the fast charging battery is important, which is the energy storage materials. But you get a fast charging batteries which cost is very high. You can't afford it. For example, a typical car is cost like 5 lakh rupees, and the battery operated car with fast charging, the equal performance cost 20 lakh or 30 lakh. You won't buy it because cost matters. So all those things are important when we try to prepare a material, when we want to design a material. And nowadays you must be reading the newspaper that the climate is a big issue. So the green synthesis is important. You have to prepare a material which can be green in the process, means the material which can follow the 12 principles of the green chemistry. Please go through and see what are the 12 principles. They are the cost, solvent, hazardous, temperature, high pressure, number of things. So there are various synthetic procedures for the materials available in the literature, and people are doing the synthesis as per facility available in their own laboratory or reported in the literature, or they discover themselves based on the need of type of materials. So this solid state, gaseous state and liquid state are 3-1. The problem with the solid state that scaling up is a challenge of the solid state material. So we want to industrialize this particular process. It's difficult. It requires high temperature because it's a diffusion controlled reaction, and then mostly they find inhomogeneous. And since we are talking about the temperature, whenever we talk about temperature, we talk about the kinetics of the reactions also. So they are not kinetically controlled. So when they are not kinetically controlled, the end product is not in your control also properly. Every time you may have the different property based compounds. Gaseous is high volume reactions, so and required good filters and cyclones, and monodispersed products are only possible by the condensation or on the surface growth. So at large scale, if you want to make this process industry viable, it's not possible. So the next thing is liquid state reaction. The liquid state reaction exists in the nature. In majority of the reactions in the nature take place in the liquid state. So liquid state or the solution methods is one of the method which can be industrially viable, and you have the control on thermodynamics as well as on the kinetics. And these reactions may not require the drastic condition based on the type of material you are preparing. For today's talk, I am focusing only the metal chalcogenides. These are the materials of the future. Very soon we will come on this point why they are metal of the future. If you can see this particular picture, it addresses most of the storage and the conservation of the energy. Fuel cell, solar cell, water splitting, which provide the hydrogen, lithium ion batteries, supercapacitors. These all are the applications of this metal chalcogenides. So what are those? These are the group 4 elements: sulfur, selenium and tellurium. Now you see these sulfur, selenium, tellurium are metalloids. They are not exactly metal or non-metal, they are metalloids, so they have the both property, which is something very unique in these materials. So you might have heard about this cadmium telluride and cadmium sulfide junctions, a low cost alternative to silicon photovoltaics, which is already in the application. Therefore, when you talk about the fuel cell, which is a hydrogen operated fuel cell, the platinum has been replaced with these materials successfully. And most interesting part of these metal chalcogenides is that they are insulators. For example, hafnium sulfide, molybdenum sulfide and tungsten sulfides are semiconductors, and niobium sulfide and vanadium cyanide are the metal-like. So these materials, these metal chalcogenide materials, are covering all three. That's one of the reason that these materials are so much prominently investigated in the lately. So when we talk about to synthesize such materials or other materials, we have to see that what are the processes by which we can make these materials. So you can see this solution process is one of the most important in entire synthetic procedures, because the moment you divert from there will be an environmental load, and then acceptability will be less. Whether you are going to physical methods or the solution methods or gaseous methods or solid state methods, the moment you divert, their acceptability will be less. So how many methods we can discuss? There are a lot more than you see in the slides. So it's always a matter of confusion which is the appropriate method to synthesize a desired material. There is no appropriate method except what you want to prepare is important. So let's go back and see. The generally acceptable process is the hydrothermal, which is the oldest method found from the nature. I'll quickly go how this found in the nature, and this is most close to the environmental processes. So what is the hydrothermal method? The term hydrothermal has its origin in geological science and was first used in the beginning of 19th century. Describing the hydrothermal circulation, this process where hot pressurized water circulated under the crust of the earth is responsible for formation of rocks and minerals. So that's the origin of hydrothermal process. This has been happening in the earth at the starting. Now the same hydrothermal process has been borrowed to the laboratory to some extent. So this is a special solothermal, it's a special case of solothermal where water is used as a solvent. Now when we call a solothermal, what is the solothermal? Normally when we talk about a hydrothermal or solothermal, the reaction temperature is above the boiling point of the solvent and above the 1 bar pressure. That's a general definition of solothermal. So depending on the type of solvent you use, it is considered, for example, if you want water, then it's hydrothermal. Lot of persons misquote this hydrothermal. They use hydrothermal everywhere, whether they are using any solvent. So there's a simple understanding. If it is a hydrothermal, water is a solvent. If it is ammonia, it is aminothermal. If it is alcohol, it's alkothermal, glycol, glycothermal. Like that you can make the terminology based on the solvent. Now if you consider it a particular solothermal process, the minimum condition is that the temperature of the reaction has to be above the boiling point of the solvent you are using, and the pressure has to be more than 1 bar, which is obviously happen when the moment you rise the temperature. So in hydrothermal what we do? So let's talk something about chemistry of the water. So what we do in the hydrothermal process, basically we are tuning the property of solvent. So water is a special solvent, and you have seen in the previous lectures also that the moment you change the temperature and pressure, its entire property change. Density, thermal conductivity, viscosity, heat capacity, dielectric constant, pressure, these are depend on the temperature and pressure. The dielectric constant decrease with the temperature. As the pressure increase, that lead to the precipitation. What is happening here? What it means that when you raise the temperature, the dielectric and pressure, the dielectric constant come down of the water. The moment the dielectric constant come down, the product get precipitated out. And this is the key behind this hydrothermal process or solothermal process. Usually the metal precursors people use in the hydrothermal process is chloride, nitrate, acetates, which precipitate out at hydroxide, and by the dihydroxide, by removal of the water, they get the metal oxide or metal particles. You can see this particular graph, which is, I don't know why it's not visible, but if you can see there's a critical point here when the temperature is close to 400 degrees centigrade and around 220 bar is the pressure. So what happens at this particular temperature, the dielectric constant is close to 10, which is like hexane or organic solvent. So at this extreme condition, the water behave like organic solvent. This organic solvent push the precipitation of a material. That's one of the reason that which is called a supercritical hydrothermal process. because at this particular temperature at 374, 400 degree centigrade or 250 bar pressure, the dielectric constant reduced to 10, which is close to organic solvent, and the water behave like a non-polar organic solvent that force the nanoparticle to precipitate homogeneously and quickly. So nowadays this supercritical synthesis of the nanomaterials is very well in practice. So in case, then what happens when it's subcritical? I am talking other supercritical, what happens subcritical? So you can see that when there is a supercritical, the nanoparticles are small in size and they quickly precipitates out. When they subcritical, the nucleation is slow and then get the bigger particles. So what will happen? Normally when people want the small size particles or nanoparticles, they always looking towards the supercritical conditions. Now this hydrothermal process has been used in the industrial process on a large scale, and this is green in nature because water is a solvent. So role of additive in the hydrothermal process. Now this hydrothermal process is not about doing the reaction in water, because water cannot be universal solvent for every material